Gravitation-Numericals from Gravitation-Chapter. This is the given information to us. First, it is saying that we have to find gravitational constant from this given data. This is given data or given, which is then we have to judge whether the given data is proper or not, or in SI unit, or in required format or not. So first is kilometer. See, we have this in kilometer. We have to convert it into meter. So 1 kilometer is equals to 10 to the 3 meters. 6.00 kilometer is equals to, see, we have 10 to the 3 and we will take this digit 64. But it already has 2 zeros, so we will add it here. This will become 64 into 10 raised to 5 meter. G, or gravitational constant. Formula: capital G is equals to GR square upon M. Substitute the values. G is equals to 9.774 into 64 into 10 raised to 5 raised to whole square, M 6 into 10 raised to 24. We can solve this by calculation by anti-log. So let us see, this has one digit, so 0 point, plus this has 2, square of 64 is 4096, so 3, 4 minus 3 is 4 minus 1 is 3, 3 point, and whatever it is in denominator, it will get subtracted, so this will be 0 point. Okay, and our powers are 10 raised to 5, raised to 2 is nothing but 10, and this will go up, so this will become minus 24. 9899 plus 2. This is 9901, and we have to see in log table. We got 6671, and after 4 digits our decimal is occurring. And also we have 10 raised powers such as 10 raised to 10 minus 24. So we will calculate, it is 10 raised to minus 14. Then this number is quite bigger, so we will transfer this decimal point 1, 2, 3. We will add 3 here. 6.671 into 10 raised to minus 11, and the unit is Newton meter square per kg square. This is our answer, and this is the basic unit, standard unit for gravitational constant. Two bodies of masses 5 kg and 6 into 10 raised to 24 kg are placed with the centers 6.4 into 10 raised to 6 meter apart. Calculate force of attraction between the two masses. What is the force of attraction between them? And also we have to find the initial acceleration. First, let us draw the rough figure. First body is of 5 kg and second body is of 6 kg. Let them be M1, M2. Then they are apart. The centers are 6.4 into 10 raised to 6 meter apart. That is nothing but R. R is 6.4 into 10 raised to 6 meter. Force of attraction, that means F. And second is initial acceleration of both of the bodies. So A1 and A2. Related to this, what is the formula we can apply? First formula is F is equals to G M1 M2 upon R square. Since it has M1 and M2 in it, we know G, we know R. So we can find out what is F. Then we can apply F is equals to MA. When we know F, we can substitute them individually by putting M1 here. We can find A1. By putting M2 here, we can find E2. So let us do the calculation. First, f is equals to g m1 m2 upon r square. So f is equals to, what is g? 6.67 into 10 raised to minus 11. This is general. Into m1. What is m1? 5 into 6 into 10 raised to 24 upon, what is r square? 6.4 into 10 raised to 6 the whole square. So just take these powers together so that you don't confuse afterwards. Into 10 raised to minus 11 plus 24, since they are in numerator. 6 raised to 2, it is nothing but 12. So this would be minus 12 since it is in numerator. What you will do, multiply these both together since they are simple. 5 into 6 is 30 upon, write down the square of 6.4 here. You can take this 0 out as well. Whatever you get the answer in power, you will get minus 11 plus 24. Raised to 1. Then secondly, what you will do is you will take this formula, F is equals to ma, but you have, since you have two bodies and two masses here, you have got the value of force. So what you will do, for body 1 and for body 2, force will be same. Just rearrange the formula as you have to find acceleration. So this will become F by m is equals to a. So you will substitute F by m1 for the body 1 and here F by m2 for body 2, and you will find acceleration 1 and 2. Got it? Force is constant here, so that's why I haven't written F1 F2 here. Mass, you have got the mass 5 A1, and here force is constant again. You have got the mass 6 into 10 raised to 24, and you will get acceleration. We have to show that the critical velocity of a body revolving very close to Earth with radius r has mean density rho is equals to 2r under root of pi rho g upon 3. How we will prove this? See, imagine you have this body rotating very close to Earth. So that means there will be no height, or the height would be very less. Height would be very near or very equal to the radius of the Earth, since it is revolving very close to the planet. So this becomes this. Also, by critical velocity we just derived it, that it is nothing but Vc is equals to Gm upon r. Okay. Let us take this as equation number 1. Also we know that mass is equals to V rho, volume and density. Volume into density. What is volume? Formula for circular body 4 pi r cube upon 3, and what is rho? We will write it as it is. We will substitute equation number 2 in equation number 1 here in m. What we will get is, we down here substituting 2 in 1, we get Vc is equals to under root of g 4 pi r cube upon 3 rho upon r. This r and this 1 r gets cancelled. We will get Vc is equals to under root of g 4 pi r square rho upon 3. See, in the question 2 and r are outside. See here 4 and r both are in square form. If we take them out of the root, so they will become 1, 2 r. Okay. What we got here? Pi rho g upon 3. Hence it is proved. Okay. Assuming Earth to be homogeneous, there is nothing changed. Determine density of the Earth from the following data. So here our data is given. We will just write it down here. Convert it into meter. 64 into 10 raised to 5 meter, right? Also we can add additional decimal point and increase one power here. This will be okay also. We have to find density or rho. Formula is G is equals to 4 upon 3 pi r rho G. Okay. From here we have to take out density. So just convert it. Rho is equals to 3G upon 4 pi Rg. Whatever it is in numerator comes in denominator. Whatever it is in denominator comes in numerator. Let us just substitute the values. Rho is equals to 3 into what is G? 9.8 upon 4 into 3.14 into what is R? 6.4 into 10 raised to 6. And what is G? 6.67 into 10 raised to minus 11. Let us take out the power first. Rho is equal to 3 into 9.8 upon into 10 raised to 4 into 3.14 into 6.4 into 6.67 minus 6 plus 11. Okay, so that becomes 10 raised to 5. You can take out the decimals or and extend the power here. Whatever is comfortable with you, you can solve it. Likewise, you can multiply the simple number and then perform antilog. If you have any doubt regarding antilog or solving, just let me know or comment down below or email me. You can multiply these simple digits and then find out what is the density. Simple multiplication and it will give you your density. What should be the duration of the year if distance between Earth and Sun gets double? Suppose first the distance between Earth and Sun was small r. What if the distance is doubled? What could be when the distance is r? The duration of the year is 365 days. Okay, but when the distance is doubled, it wouldn't be double of 365. Okay. Let us write down what is given to us. We know that first in time duration, the time of the year in this distance is 365 days. Condition given to us is what if the second distance is double of first distance. Okay, that means we will get a ratio R2 upon R1 is equal to 2. Correct? We have to find time period, second time period. Okay, T2. What is the formula we can apply? By Kepler's law, T2 upon T1 the whole square is equals to R2 upon R1 the whole cube. We know the value of T1, then we know this ratio, so simply we will substitute the values. T2 upon what is T1? 365 the whole square is equals to what is the ratio given to us? It is 2 the whole cube. So this will become T2 upon 365 the whole square is equals to 8. What we can do, we can transfer this square and make it under root of 8. This will become T2 upon 365 is equals to under root of 8. See, if you see in this table here, in square root table you will get under root of 8 as 2.828. Simply you have to T2 is equals to 365 into under root of 8. That will be 365 into 2.828. Simply after multiplication you will get what is T2. The distance of two planets from Sun are 10 raised to 13 meter and 10 raised to 12 meter. Here I have constructed a rough diagram. You can also construct a rough diagram. You will get, this is presentation skills, and it would really impress the examiner, and it will help you also in imagining things. You find the ratio of time periods and orbital speeds. What are the ratio? That is T1, T2 upon T1, and orbital speed, with which speed, what speed the two planets are revolving. That means critical velocity. The given data to us is R1 is nothing but 10 raised to 13 meter and R2 is nothing but 10 raised to 12 meter. We have to find first T1 upon T2, that is the ratio. Second, orbital speed, that is Vc1 upon Vc2, since there are two planets. Formula for first one is, we know that T1 upon T2 the whole square is equals to R1 upon R2 the whole cube. For critical velocity, we know that it is under root of gm upon small r. Why not capital R? Because here we are not taking any planet or accountants of this. So we are, first calculation, T1 upon T2 the whole square is equals to R1 upon R2 the whole cube. Don't know both of them. What we will do, we will transfer this square here and it will become 3 by 2. T1 upon T2 is equals to R1 upon R2 raised to 3 by 2. Okay, what is R1 upon R2? It is nothing but 10 raised to 13 upon 10 raised to 12, which we cancel, we will get 10 raised to 1. So this will become nothing but 10 raised to 3 by 2. Like the previous numerical, here it is asking what would be the duration of the year if the distance between Earth and Sun becomes half the present distance. So what is given to us? It is given to us first the time period what we have in the present distance of Earth and Sun. The duration of the year is 365 days. Then what it says that R2 is equals to R1 upon 2. That means R2 upon R1 is equals to 1 by 2. Okay. We have to find T2 or time period second. What is the formula? T1 upon T2 the whole square is equals to R1 upon R2 the whole cube. We have got T1 here, R1 and R2. So let us substitute. 365 upon T2 the whole square is equals to 1 by 2 the whole cube. So this becomes 365 upon T2 is equals to 1 by 8. What we will do, we will transfer this square and make this 8 root 8. Since root of 1 is 1, so this becomes 365 upon T2 is equals to 1 upon root 8, but we need T2. So T2 is equals to 365 into root 1 upon root 8, a value of root 8 and divided by 1. It is 2.828 divided by 1 and multiply with T2. You will get the duration in days. Radii of orbits of two satellites revolving around the Earth, their radius are in ratio 3:8. We have to compare their critical speeds and periods of revolution. Critical speed, that means Vc, that means under root of gm upon r. Period of revolution, that means time period T1 upon T2. Let us write down what is the data given. First is ratio of the radii R1 upon R2 is 3 by 8. Have to find first critical speed. Second, we have to find T1 upon T2. What are the formula? First, we have Vc is equals to under root of Gm upon R. For second, we have the formula T1 upon T2 the whole square is equals to R1 upon R2 the whole cube. First one for critical velocities. Vc1 upon Vc2 is equals to under root of Gm upon R1 upon G under root of Gm upon R2. We can write it as Vc1 upon Vc2. G and G gets cancelled. M1 M2, this is M1 M2. So this is under root of M1 upon R1 into under root of R2 upon M2, reciprocal. So that means Vc1 upon Vc2 is equals to M1 upon M2 into R2 upon R1. Arranging, since both the satellites are orbiting Earth only, so that their M would be also equal. M is equals to M1 and M2. So Vc1 upon Vc2 is equals to under root of M into R2 upon M into R1. M and M gets cancelled. What is R2 upon R1 given to us? It is nothing but we are given R1 by R2. So R2 upon R1 would be reciprocal 8 by 3. Just go and find out what is under root of 8 and what is under root of 3 and just equate them in from the log table. This is to is this. So this is the ratio. This is how you will write the ratio. For second one, here we are given the information that we have to calculate the height of the communication satellite. The communication satellite which revolves around the Earth 24/7. So here information was given, so I have just wrote it down. Also the time period, the time taken by the satellite is, it revolves around the Earth 24 hours and also it revolves 60 minutes and 60 seconds. So we will convert it into this form and we will substitute the values. We have to find its height. Remember the formula we derived. T is equals to 2 pi under root of R cube upon Gm. Time period of a satellite revolving very close to Earth or at a certain height. We will use this. We will take this as the satellite is at certain height. So there will be some addition to it, R plus H, capital R plus H, which would be R. So we will take it outside. We will remove this root. So this all rest of the part will become square. T square is equals to 4 pi square R cube upon Gm. We will remove this R cube and transfer it here. So this will become R cube is equals to T square Gm upon 4 pi square. But we know that since the satellite is at certain height, that means small r is equals to R plus H. So we will substitute it here. That becomes capital R plus H the whole cube is equals to T square Gm upon 4 pi square. I will show you how we are going to find the height later on. Let us substitute the values first. What is T? 24 into 60 into 60 the whole square. What is G? 6.67 into 10 raised to minus 11. What is M? 6 into 10 raised to 24, and what is upon 4 into 3.14 the whole square. You will solve this equation and you will get a number here. Then whatever you found out, it was r plus the value of r plus h the whole cube. Okay, what you will do, you need r plus h or h, not h cube. You will transfer this cube here and this will become cube root. R plus h is equals to cube root under root of whatever the number you got. Then you will get the value of r plus h after undergoing cube root. But you need the value of h, so you will keep h here, whatever number you got, and minus r, capital R, you have the value of it. H is equal to whatever the number, and r you have 6.4 into 10 raised to 6, and then you will get whatever the answer in meter form. You will convert it into kilometer. Convert meter into kilometer, and the final answer would be in kilometer. Since you cannot see that the satellite is revolving this much at this much meter height from the Earth's surface or planet surface, no, because Earth is very large and the distance and the height a communication satellite has to achieve would be in kilometer. In meter it is not scientifically possible. A body weighs 4.8 kg weight on surface of the earth. Weight of the body on earth is 4.0 kg. What will be its weight on surface of a planet whose mass is 1/8 of mass of the earth and radius half of the earth. The given conditions, let us write out what is given to us. First is weight on earth is 4.0 kg weight. Okay. Then we are given a ratio that the mass on that planet is 1.8 to the mass of earth. That means mp upon me is equal to 1/8. Then same ways, rp is equal to half of mass of earth. That means rp upon re is 1/2. What we have to find? Weight of the planet. Weight of the body on the planet. Formula is Wp upon We is equals to mp upon me into r p square upon rp square. We have got We, this ratio and this ratio. Let us substitute it. Wp upon, what is We? 4 is equals to mp upon me 1/8. Re upon rp, that is 2. 2 upon 1 the whole square. So we will get Wp upon 4 is equals to 1/8 into 4. So we will get Wp is equals to 1/2 into 4. If we cancel, we will get 2. So weight of the body on the planet is 2 kg weight. We have to just find binding energy of a body which is of mass 50 kg at rest on the surface of the earth. Suppose you have a friend, he weighs 50 kg and he is resting on the surface of the earth. So you can find out the binding energy acting upon him. So these are the points, whatever the data was given, I have copied down. Small m is the mass of the body. We have to find binding energy. Okay, formula for binding energy is capital Gmm upon R. Let us just substitute it. Binding energy is equals to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 into 250 upon, what is that, 6.4 into 10 raised to 6. Simply by solving you will get binding energy in joule. We have to find total energy and binding energy of a satellite which has mass 1000 kg, which is orbiting in height 1600 km above Earth, and this was the information generally. GRM was given. I have written down M here. What is the height? It is given in kilometer. When we are converting R in meter, so we will convert it also. It would be 1.6 into 10 raised to 6 meter. Total energy first, minus GMM upon 2 upon R plus H, and for binding energy it is minus of total energy. What we got, G is 6.67 into 10 raised to minus 11 into, what is M? 6 into 10 raised to 24. What is small m? 1000 kg. You can write it down as 10 raised to 3 also. And 2, what is R? 6.4 into 10 raised to 6 plus, what is height? 1.6 into 10 raised to 6. First solve the bracket, then multiply it with 2 and you will get your total energy in negative form and in joule. Then for binding energy, one step ahead. Binding energy is nothing but negative of total energy. You already got your total energy in negative, so negative becomes positive, and this will be your total energy, binding energy in positive. You have to calculate here escape velocity of a body which is getting removed from the surface of the earth. Here mean average density is given to you, and also this general information. So what is the formula for escape? We have to find escape velocity. Formula for escape velocity is 2r under root of 2 pi rho g upon 3. Let us just substitute it. VE is equals to 2 into, what is r? 6.4 into 10 raised to 6 under root of, what is 2? This is 2. 3.14 into, what is rho? 5.5 into 10 raised to 3 into, what is g? 6.67 into 10 raised to 11 upon 3. Solve what is there and in under root, and then multiply it with these numbers, and then you will get your escape velocity in meter per second.